So in this short lecture, I want to look at circular motion and pretty much something called uniform circular motion. And this is where an object travels at a constant speed in a circle. All right, so the reason we're looking at this is that if I draw, say, a circular path, maybe I'll just draw a dotted line for now. And this object is at, say, this location, this location, this location, this location. I'll even add some more. And we know that the object has a tangential velocity at any of these locations, where we can define, let's see, tangential. Whoops, something I got. There we go. Tangential velocity to mean that an object has a speed at that point in a line tangent to the circle. So a straight line tangent to the circle. So we can think of this as the linear speed, the linear speed of the object at a location. And this tangential velocity points tangent to the circle. Hopefully you can see that. I can try and zoom in a little bit. So linear speed of the object at a location, and it points tangent to the circle. So I think in the textbook they might abbreviate this VT for velocity tangential. A lot of times we're just going to use V. We're not going to worry about it. We're going to assume it's the tangential velocity. And but I just thought I'd let you know that in case you see in the textbooks or in the textbook VT, and specifically in the reading over this that I'm going to give you from this Serway and I think it's Fawn or something, I can't remember. But from this text, yeah, like right here, they like to write V sub t for velocity tangential, and I'm just going to write V. I'm not going to worry about that. So V sub t or velocity. Why even have the t on there? Probably to differentiate from, I don't know. I was going to say rotational velocity, maybe. I'm not sure. I don't see it a lot, to be honest. So I'm not sure why they just feel like they just want to remind you that it's tangent velocity. So if I draw this tangential velocity, let me go ahead and pick a color here. Such a hard choice. All right. If I draw this tangential velocity, and maybe this object has a rotational velocity or an angular velocity where it's moving like this. And so this would be counterclockwise. And going about the circle counterclockwise, just driving in a circle. Maybe it's a car driving in a circle. that we have the car has a tangent velocity. Maybe the car is this blue spot, and it has a tangent velocity at any of these locations as it travels in a circle. And it's going to be a constant velocity because this car, say it's going 25 miles per hour in a circle, and in all these locations, it has a tangent velocity, which is a straight line tangent to the circle. And we also should notice that the that I'm drawing, because it's a constant velocity, I'm drawing all these vectors the same length. Trying to, at least. All right. So what you have is uniform circular motion then. And a question comes up where if this is a, and I can write a description here, blue dot is a car traveling at a constant speed, at a constant 25 miles per hour in a circle. And we know that the orange vector is the tangential velocity. So this orange vector here, I could call this one right here. If I just look at one of these, I could call this one V1, and I could call this one, let me write that again. I call this one right here V2. All right, so a good question would be, well, what is the acceleration of this object? And right away you would say, well, it's not accelerating because it's it's a car traveling at a constant speed in a circle. But let's look a little closer at it. What we have, and maybe we want to know the acceleration between V1 and V2, between this time period right here. We should remember from earlier in the year that acceleration is equal to delta V over delta T. And delta V is equal to VF minus VI. And delta T we can, call TF minus TI. Right now I'm just going to leave it delta T. All right. So up above, I have two velocity vectors, V2 minus V1, right? And obviously one will be initial. And I want to take a look at that acceleration between velocity 2 and velocity 1. Okay, so, if I subtract V1 from V2, so V2 minus V1, we know that that is the same as saying V2, right? This is vector V2, vector V1. This is the same as saying V2 plus negative V1. So if I can just find negative V1, I could, understand this acceleration a little bit better, which that we think is constant. So if we go back up to the circle, we can see that V2 or V1, I think we're doing V2 minus V1. And so if V1 points to the right, then negative V1, right? Let me draw this in another color. Negative V1 would point like that brown vector right there. So all I got to do is add that to V2, right? So I have V2, which looks like about, let's try and draw at the right angle, something like that. And I have negative V1, which, all right, that I'm going to put head to tail. Kind of like that, right? And I'm just going to add these two together. Well, if you remember, when we add vectors, we put them head to tail. That is going on right there at that red point, right? The head of the brown vector is at the tail of the orange vector. Then we find the beginning of this treasure map, and we start here, and we end here. And so we draw our resultant start to end. We take a dotted line, whoops. Take a dotted line like this, and point it just like that. And maybe I'm going to draw this in red. So what I have there is V2 plus negative V1, or V2 minus V1. And what I have there is actually the acceleration vector. And I'm going to call it A sub c right now. And then I'm going to go back up to the triangle, the circle, and show you where that would go. So that is the acceleration. You could say, you could say halfway between those 2 points, right? So it's the acceleration. If I can draw the dotted line right there. And so that's kind of interesting. That's pretty dang close to the right angle. All right. So what we have is an acceleration right there. And if I would have picked a couple different points, what if I would have picked, say, what if I would have called this VF, right? And this VI. And I tried to, I said A equals VF minus VI over T. So I just got to say that that's VF plus negative VI, right, over T. Hopefully you can see that. And all right, so VI points like that. So negative VI would point like, let's see, like this, right? And so let's just add, let's see if I can draw this maybe off to the side right here. So I'm saying I have VF pointed like this, and I'm going to add it to negative VI, which is going to be head to tail with this orange vector. How am I going to do that without... Okay, I think I can just do it like this. So I'll just draw that right there. And you can see, hopefully, I have a start and an end to this treasure map. And then a straight line drawn start, a dotted line drawn start to end, pointing start to end is going to be, if I was to go back and label this was VF, right? And this was negative VI, and I added them. And so this red dotted line is A sub c. So let's go ahead and put that acceleration on our circle. So between these 2 points right here, so maybe right, let me see if I can get that angle right. So maybe something like that right there. And let's see if we can spot a pattern here. We got two of these now on our circle. And what if we take 2 more? What if I took, say, this point right here and this point right here? Can you see that? And maybe called V1. Called this, maybe I should give these new names if I do this. Yeah, I'll just give them new names right now because otherwise I think it's going to be confusing. V1, I'm going to call, I'm going to I'm going to call this VF now. I'm going to call this VI over here. So this will be my VF pointed right, and my VI will be right here. So if that was the case, what would happen? Well, then we have a, once again, VF plus negative VI. Negative VI would point like this. VF would point like this. Maybe I should draw that in orange just so you clearly know what I'm saying here. Right, we called VF that down there, right, V1. So it just points to the right. And VF plus negative VI. And you can see I have a start right there and an end right there. And my dotted line points start to end. We'll call that A sub C. And that's going to be halfway between my final velocity right here at 6 o'clock and my initial velocity at 9 o'clock there. And so halfway between would be about 7 or 8 o'clock right there. And check out what we're seeing. Let's see if we can see the pattern now. That when an object is traveling at a constant speed in a circle, it is accelerating. That even though it's going 25 miles per hour around a circle in something we call uniform circular motion, that it has this acceleration that is center seeking. And this is what we refer to as centripetal acceleration for center seeking. So let's go ahead and write that down. Centripetal acceleration. Let's see. Center seeking. Acceleration. That allows an object to move in a circle. All right, go ahead and jot that down. So an interesting question here is, how is this acceleration, right? So what we're saying is uniform, because the car could be speeding up, right? The car could be going in a circle and accelerating. That's definitely possible. But what we're saying is the car is not doing that. The car is in uniform circular motion. And we're saying that this is, sorry, that's an E, dang, is accelerated motion. All right. Let me highlight that. So uniform circular motion is accelerated motion. And the question becomes why? How is that possible? That you're traveling at 25 miles per hour but still accelerating. And the idea is go back to your definition of what acceleration is, right? Acceleration is a change in velocity. And you have to remember what velocity is, right? Velocity is a vector. That has magnitude and direction. And you would be right to say that your velocity isn't changing its magnitude, right? it's 25 miles per hour the entire time. So the magnitude doesn't change. But the direction does. And this is why this is accelerated motion. Let me write that. Okay. All right. Okay, so what we're saying is that there has to be a center seeking acceleration in order to turn in a circle. And this is confusing. Because let's say you're traveling in your car and you're about to turn off of Redmond into the school, right? So you're going to make a right turn. You're right by the tennis courts. You just go past them, and you're about to turn into the school, and you turn like this and like this into the school, but you take the turn a little fast, and maybe you have your water bottle or a coffee cup or some, just sitting in your console there, and it spills on you. It actually, you're driving and it tips over and lands on you. Not only that, it goes flying and hits your leg because you just, you're taking this turn just way too fast because you're just in a little bit of a hurry, and you shouldn't be driving that fast, but the coffee cup tips over and hits you. It actually flies out of the console and hits you, and you spill coffee all over, right? So what the heck, right? You're like, well, it seems to me that if I was to draw the coffee cup, maybe this is the coffee cup, that the coffee cup goes from the center of the car and flies to the outside of the car. And you're like, Mr. Rodriguez said there's a center seeking acceleration when you travel in a circle, but it seems to me like watching this coffee cup that objects fly out to the outside when they're traveling in a circle. And it seems to me like there should be a center fleeing acceleration. And let's go ahead and get a little more paper here. And you'd be like, well, maybe the center, let me maybe call this a different name, centrifugal, right? So I'm going to say centrifugal, but it sounds like centripetal, but it's not. So I'll say centrifugal right now, just so you can tell the difference. So this centrifugal acceleration is center fleeing. Oops, that's an L. And how do you deal with this? How do you I'll make this a green car. How do you deal with this, right? Like, what is going on here? So, what we're saying in physics is that centrifugal or centrifugal is how I would actually say it, but centrifugal acceleration doesn't exist. The reason that the coffee cup spilled is that it didn't have a centripetal, a center-seeking acceleration strong enough. Whoops. To make the turn. So let's clean this up a little bit. So we're saying once again that centrifugal acceleration doesn't exist. The reason the coffee cup spilled is that it didn't have a center-seeking acceleration strong enough to make the turn. So we're saying it didn't have enough force directed into the center to make this turn. It didn't have enough acceleration from a force, so a centripetal force. Where would that force come from? Normal force, maybe from the console. Whoops, dang. Maybe, so, yeah, it didn't have enough Fn from the side of the console. You could have said it didn't have enough force friction. It needed some force there to generate the acceleration. And I'll just write not enough. And let's remember that that center-seeking acceleration is called centripetal. Centripetal. Whoops. All right. And so you're sitting there saying, well, but it was flung to the outside. There was a force causing it to flee. What is that? So how is that possible? Well, what we're saying is that centrifugal, right, force is actually just inertia. So an object stays in motion unless acted upon by an external force, right? An object in motion stays in motion unless acted upon by an external force, Newton's first law. And what you can see is that the coffee cup didn't have this center-seeking force. So what did it do, or what did it try to do? The coffee cup tried not just to fling, didn't really try to fling to the outside. That's not what it tried to do. What it really tried to do was to keep going down flat. The coffee cup is like, well, why would I turn into the high school? I have inertia. I have a tendency to keep moving in a straight line. Why would I turn right? And until the coffee cup gets a normal force from your leg or a normal force from the side of the car, and the coffee cup is like, oh, okay, I will turn right and go into the school, right? And so this is the idea. Centrifugal, center-fleeing acceleration doesn't exist. It's really just inertia. God, what's wrong with my stylus here? It's not wanting to write. Okay, and that's the key idea. It's really just inertia. An object wants to keep traveling, and wants to maintain its state of motion, and that's all that's going on here. So do not confuse the two, even though, in chemistry class, there in the medical lab, there's such a thing as a centrifuge, which cause you spin something in a circle, and the heavier particles go to the bottom, go to the outside. But really what that is they're just trying to travel in a straight line, and so they get separated out that way, based on their mass being more massive, and having more inertia, because mass is proportional to inertia. So there really is no centrifugal force. And sometimes you hear it referenced in physics because it's nice to be able to talk about this with a word, to have a word to describe the inertia that you experience, right? This experienced force. So you can say that we could say it this way: centrifugal acceleration or a force, I'm going to call it force right now, is a perceived force. Caused by inertia or an object's tendency to to maintain its state of motion, right? Okay. Good. Let's go a little further here. And I am going to I was going to this video is already getting kind of long. I was going to explain where this formula comes from, but now I don't think I'm going to. And if you want me to show you, or maybe I'll do it quickly. Yeah, maybe I'll just do that. What it is and what we have here. Okay, so if we look back up at say our circle, and we have let's say an object's location. This is its initial location, and let me see if I can draw this decently. And this is its final location, and it's traveling in a circle. This is roughly, this distance here is roughly delta x. It's displacement. The closer these 2 points get together, the closer that gets to being a straight line. So it's decent enough. It works. The angle here is this angle right here, and this distance is the radius of the circle, and we can call this theta. We can also look at maybe the velocity vectors for these two locations being here. That would be V1 and V2 being here. Get a little crazy with that line. And we can say that, let's see, negative V1 would point like, point like that. And V2 plus negative V1 would look like, let's see here, V2 negative V1 look like this. Ugh, this is getting gross. All right, something like that. And the acceleration right, would be something like that. My drawing's a little rough, so I'm kind of correcting it here. The acceleration would look like that. Okay, so kind of what we're saying, and this would be theta, and these are similar triangles right here. This triangle in yellow is similar to this triangle. All right, and because of that, we can set up a ratio. We can say the ratio, right, of how do I want to say this? Maybe I should call this. Maybe I should say it like this. I'm gonna call this delta v. All right, so I'm not even going to call it acceleration. I'm going to call it delta v. And what we can say is that delta v is similar to delta x, right? And I can write that like this. Or I can say it this way. I can say delta v is to a side of it. Delta v is across from theta, is to one of these sides, v1 or v2, which they're the same magnitude. So I'm just going to call them v. So I'm going to say this is v, this is v. I'm going to say delta v is to v as delta x is to r, because delta x is across from theta. All right, then I'm going to remember that v is equal to delta x over t, and draw that right there. And in that delta x is equal to v times t. I'm going to make the substitution. So I'm going to say that delta v over v is equal to, I'm going to sub in this guy right here, right? For delta x, v times t. So instead of writing delta x right here, I'll write v times t over r. Multiply both sides by v, right? And cancel. Over here, I'm going to get, or have delta v. And why don't I call this delta t? Right? I can do that. This is actually delta t. That's fine. Let's go ahead and put a delta right there. And okay, and rewrite. So we have delta v is equal to v squared times delta t over r. And then divide both sides by delta t. And what that creates over on the left here, we should recognize that delta v over delta t, this is acceleration. And in fact, this is for an object moving in a circle. We're going to call this centripetal acceleration. And that's equal to, what's over here on the right? V squared over r. Okay, usually most years I don't derive that. Don't worry about it if that didn't make a lot of sense, or if you want to go back up and look at it again and see how it makes sense, you can. But that's the important part, is you understand that when you're moving in a circle, that acceleration, that accelerated motion, that centripetal acceleration is represented by this formula. A sub c equals v squared over r. Okay. But you might have noticed back in my explanation that I kept saying force, right? I kept talking about forces, that the coffee cup didn't have enough centripetal force. And in this, getting at the idea that Newton's second law said that for every force, we like to set it equal to a mass times an acceleration. And here we can do that with centripetal acceleration. So we'll call this centripetal force. We'll call this centripetal acceleration. And we can write this equation this way. And we can sub in v squared over r, right, into a for a sub c. So sub in for this right here and rewrite this way. F sub c equals mv squared over r, right? And it doesn't matter. I put the r, the m on top and drew the bar a little larger. That's fine. Okay, so whoops. All right. So here's two equations for centripetal force. Hopefully you can see that. Let me go over a little bit more. Okay, so when I write F sub c, I mean centripetal force. Okay, so finally, I guess the end idea here would be that this is not a new force. So force centripetal not a new force. Meaning that it comes from other forces. So we never draw this on a free body diagram. So it comes from other forces. And how does it show up then? How does it show up in our equations? Well, as those other forces, but then it also shows up as the net force. So we like to say maybe something like this for circular motion. Maybe we say sum of the forces in the x direction equals max. And we said that this is F net, right? This is the net force. Well, that is also going to be our force centripetal. That force centripetal is sigma Fx, right? It is those forces. So when we set up this equation, right, that this is true, that force centripetal is the net force. So we might end up saying something like this. We might end up saying sigma Fx is equal to mv squared over r. Because what I'm trying to say here is this is your net force, or is your centripetal force. And to go along with that, then this right here, this AX, is centripetal acceleration. Assuming the object's traveling in a circle. And a lot of times I like to call into the center positive x for the direction, which is kind of weird, but it works pretty well. And all right, so this is kind of a lot coming at you at once here. Once again, you don't have to know this derivation right here. Don't worry about it. Just understand that these are our new equations right here. A sub c equals v squared over r. F sub c equals m times a sub c. F sub c then can equal mv squared over r. Let's do an example and then we'll call it good. If we look at down here from practice A, it says, let me add a page here so I can write right above this. Move that. Okay. All right, a rope attaches to a tire on an overhanging tree limb. So let's do one example problem, just because I feel like I've done a lot of talking and maybe a actual a problem would help more. So we have a tire or a rope here attached to a tire. and a girl swinging on the tire has a centripetal acceleration of 3.0 meters per second squared. All right, so we got a kid who's swinging on a tire. I don't know if I can draw the person, but I'll try. That's kind of terrible, but all right. You get the idea. And they are swinging in circular motion. Let me try and draw a little bit better. Nice. I erased too much. Okay. All right, that's a little bit better. So when the kid swings back and forth, they're not going to swing in an entire circle. But even just swinging back and forth like this is a segment of a circle. This is an arc length of a circle. And so this counts as circular motion. This is true maybe if a car is driving over a bump in the road, a hill, cresting over a hill, going into a valley. That can be circular motion if you think of that as a piece of a circle. And so you can see some interesting problems this way. They say that the girl swinging the tire has a centripetal acceleration, and I'm just going to draw it on here, right, of 3.0 meters per second squared. And so this acceleration is going to be directed towards the center of the circle, which is going to be straight up. Because you can see the circle I'm trying to draw, right? You can see the dotted line if you continue it around, and it creates a circle, and the center would be up here above this tree limb or something. Well, actually, it'd be at the tree limb itself. It would be right there, because that's the length of the rope, which would be this length of the rope is the radius. So this is R. And then they say, if the length of the rope is 2.1 meters, what is the girl's tangential speed? And so maybe the tree, maybe it's right now it's going, I don't know. We'll say, I think I have more room this way. So we'll say that she's going counterclockwise right now. So this is VT, or if you just want to write just V, you can, and that's fine. And we want to know what this tangential speed V is. So this is the question. And so we just go ahead and set up our equation, which we should remember from above, hopefully. If not, that's okay. You got some problems you can do to work on that. A sub c equals v squared over r. We do know the a sub c. I don't know why I didn't write it down. Just starting to get tired after making this video, I guess. All right, it's 3.0 meters per second squared. Okay, so we have a drawing, everything's labeled, and then we find our equation, a sub c equals v squared over r. Plug in what we know. We know a sub c is 3.0 meters per second squared, of course. Acceleration units are the same, even though it's centripetal acceleration. V, we don't know. R, but it does get squared, and R is 2.1 meters. So the next thing I'm going to do is just solve this equation. Multiply both sides by 2.1, then square root. You can see the 2.1s cancel, the meters cancel. We're left with v squared is equal to, what's 2.1 times 3? That's 6.3. Yeah, 6.3 meters. The meters get squared because a meter times a meter is a meter squared, and over second squared, which is important because we're going to square root the 6.3 and square root the meters squared over second squared to get meters per second. All right, so we do that. Now I got to get my calculator. Luckily, I got it right here. Let's see. Square root of 6.3 is equal to 2.50998. So we're going to say we'll say V is equal to 2.51 meters per second. All right. And there, that is our answer right there. Whoops, I was going to highlight, dang. That's our answer right there. All right. So there you go. There you have it. Hopefully this is making sense. And like I said, we'll do some practice and improve on it. All right. Have a good day.